Good recording.
Okay, great. So we're looking to construct a process with these three properties, and here's one way to construct it, just to convince you that such a process exists. So first of all, we know that this process, so this is the t-axis, and this is the bt axis. We know that this process is always going to be on one of these two lines because of property 2. So, you know, it can either be on them or jump between them. And I guess the way that makes the most sense to construct it is just take an actual Brownian motion and what we can do is try to kind of change the time, or maybe, okay, let me formally write it and then explain what I'm writing. So let's define tau of t to be the minimum time. So let's suppose that W of S is an actual Brownian motion in R. And define this continuous sequence of stopping times. Tau of t is just the minimum S such that W of S in absolute value is equal to t. So look at the first time where the Brownian motion reaches any t by absolute value, and then define, you know, B of t to be just equal to W at tau of t. So to know where my process B is at time t, I look at the first time that the Brownian motion hits t in absolute value, and I look and I see if it was plus t or minus t.
Ronen, it might be good to remind people a little bit about Ronen motions, because this is like a new character in this lecture series. So if you're using some properties of it.
Right. So I think what I'll do is I'll just give an alternative definition for this process, because I don't want to. I mean, yeah, I think if you're okay with Brownian motions, then this is a good way to define it. But otherwise, I think the best intuition is just. Do you think Poisson point process is fine, or this is also something that? Okay, let me write an alternative definition. Okay, but first, I mean, I just to draw a picture, you know, so this process really goes on these lines, and once in a while it jumps up or down like this. And these times where the process jumps, this is a sequence of times between 0 and 1. Let's denote this by J sub I. So this is the set of times where B, T, I jumps either from minus T to T or the other way around. And J sub I is going to be a Poisson. I'll define this in a few seconds. A Poisson point process with intensity 1/2t. What does this mean? So this means that so Ji is a random subset of the interval 0, 1, and it's uniquely defined by the following properties. So the expectation, so it's uniquely defined by the two following properties. For every subset of my time axis 0, 1, the expectation of the number of jumps intersected with this set, the number of jumps inside this set, is going to be equal to the integral of over the set A of this 1/2t dt. And the second property that uniquely defines it is that if A and B are disjoint, if A and B are disjoint, then Ji intersection with A and Ji intersection with B are independent. Okay, so I mean, if you want, you can just think about, it's kind of like, okay, I guess you can either take a Poisson random variable. Okay, it would be much easier for me to give an alternative definition if this integral would be convergent and not divergent. It's divergent near 0. So except for some issue near 0, where near 0 we're actually gonna exhibit infinite many jumps in this little thing here. Except for this, we can kind of think, take a usual Poisson variable and then generate the locations of the jumps uniformly. Okay. But I mean, an important property that we'll have is that given that we know everything that happened until some point in time, what's going to happen in the future, the locations of jumps in the future are going to be independent from what we saw so far. Okay? Good. So
and jumps are becoming more and more rare as we
yes, they're becoming more and more rare, and t only goes up to time 1. So when we get to time 1, the rate is like 1/2, and near 0 the rate is much faster. Which kind of, okay, I guess it kind of makes sense with the fact that this is a martingale, because if okay, let me
and the intensity has to be this 1/2t to be a martingale or something.
Exactly, that's the intensity you have to pick for this thing to be a martingale. Exactly. Yeah, and like the only thing that we didn't quite that's not quite well defined is that I didn't tell you what's the value of BT at the time of the jump. Is it left semi-continuous or right semi-continuous? At this time where I have the jump, is it equal to, this value or to this value? But it's not gonna matter, and this is why I'm not even gonna tell you. I mean, it's really a technical issue that's not important. Okay. So now here's so some facts. The first fact is that obviously B at time 1 is uniformly distributed in the hypercube, right? Because every coordinate is a martingale. So for every coordinate, I have, 50% chance to be +1, 50% chance to be -1. Everything is uniformly distributed. 2, if I look at f of b of t, okay, just to remind you, we started with some fixed function. We took this multilinear extension, and then as the argument to this multilinear extension, I'm taking this, strange jump process. Then f of b of t is, it's the sum of those things evaluated at b of t. So, let's write it. So this is the sum over subsets, the Fourier coefficients times
Ronen, I have a question, just to make sure, because I don't really know Ronen motion that well. Is it independent in each coordinate?
We defined it so that it's independent in each coordinate. I only told you how to construct one coordinate, and then I told you take all coordinates to be independent.
All the coordinates are ID. Okay.
Yeah. This is and now this product, well, this is a product of IID martingales. A product of IID martingales is itself a martingale. Okay? So every summoned here is a martingale. So it's the sum of martingales. So this entire thing is a martingale. Okay?
Was it important that they are IID or just that they're independent?
Just that they're independent for this purpose, right?
So you could maybe imagine like taking different processes on each coordinate. Not that I see how.
Yeah, it looks like it would be a lot of fun, but I don't know how. Yeah, it's possible. Okay. So maybe now let me just repeat what I told you during the break. There are many martingale proofs on the discrete hypercube where we consider a slightly different kind of martingale. So if you look at this jump process, it's kind of a strange way to sample from the uniform measure in the discrete hypercube. We're basically sampling from the uniform measure. We don't sample everything all at once, but we introduce some time axis and we sample more and more bits of randomness as time continues, as time increases. There is an even more natural way to introduce time axis in this setting, which is just sampling coordinates one by one, right? Instead of sampling all the coordinates together, we can sample coordinates one by one, and then we can look at the corresponding martingale that we get. So, we can look at the martingale MI to be the expectation of F at, x, which is uniformly distributed, conditioned on x1 up to xi. Okay, I put this in brackets. We're not going to do this, but you've probably seen at least one proof where this is what you do. You sample coordinates one by one. Your time axis is this, coordinate sampling, and you consider the Martingale where I have this coordinate filtration. What we do here is we also introduce a time axis, but instead of sampling coordinates one by one, we sample all the coordinates together, only we kind of add the randomness infinitesimally in some sense. So now our time axis is continuous, and when we go from t to t plus a very small dt, most chances are no coordinate at all is going to jump. But there are some chances that one of the coordinates is going to jump, and whether or not a coordinate jumped and which one jumped, this is basically the randomness that we're adding. Okay, so you can also think about this, as time goes from 0 to 1, I have more and more entropy for my I have more and more mutual information between my location and the final location. I kind of continuously add more information. Okay, so this is what's going on, and the analysis is going to take derivatives of this process f of bt with respect to time. Okay, so here's a useful fact about martingales, and for this fact, I need a definition. The quadratic variation of a stochastic process or a martingale. So suppose MT is some stochastic process. Actually, okay. The definition is really deterministic, but we're going to use it for stochastic processes. We define M in those square brackets T to be the supremum over sequences of times, increasing sequences of times, T1, T2, etc., up to T of the sum, or maybe it's, so those are not infinite, it's up to Tk, which is at most T. The sum I goes from 1 to K of M at, maybe let me put this T not as a subscript, but in brackets so that it matches what we have above, M of Ti minus M Ti minus 1 square. So it's, it's almost like the total variation of this process viewed as a function, only I put a square here. I look at the sum of the squares of the differences of M. Okay? So this is called quadratic variation, and
so T0 is 0 and Tk is T maybe? For this
yeah, T0 is 0 and Tk, I mean, Tk can be equal to T if you want. Doesn't matter, equal or small or equal. I mean, it actually matters if the process is not continuous, but yeah. So a useful fact is that if MT
Is the soup also overall K?
The soup is also over all K. Yeah, it's over K and also over the T's. Yeah. If empty is a martingale, then the variance of M at any time T is equal to the expectation of the quadratic variation at time T. Okay, the quadratic variation is a deterministic quantity. I look at its expectation. Sorry, the quadratic variation is a random quantity, but it only depends on what the process looks like. I look at the expectation, and this is going to be equal to the variance. Yes, exactly. It's any bounded K. It's the supremum over bound. Yeah, maybe let. Right. Questions about this fact? Okay, so, you know, we're...
Question from Gregory Rosenthal asking, should it be infimum rather than supremum?
Should it be infimum? No, it should actually be supremum. The infimum is like, no, I mean, it's a, wait, am I confusing? Yeah. For us, as long as they're increasing, it's fine. Yeah, I see what. Yeah, thanks. I mean, it's a. I mean, maybe let me just say that the partition should become denser and denser. Yeah, I mean, this definition is not quite correct. For us, it's correct, but let's say that so as I'm taking the supremum, I want the difference, the consecutive differences to go to 0. Yeah, sorry about that. Okay. You know, it's like, just think about this like, you know, it's like a Riemann integral. It's the same limit as we take in a Riemann integration. Only we consider the differences. Okay, so just to recall, what we're interested in is upper bounding the variance of f at b of 1. All of the above theorems give an upper bound for the variance, but now given this fact, we can actually write a nice expression for what this variance is going to be. And the variance of b of 1 is just going to be, so let me write this as a claim. From now on, I'm going to, I guess, do a lot of hand waving because I don't have time to make things very rigorous, but I'll try to give you some intuition about what's going on. So the variance at B of 1 is the quadratic variation. And for jump processes, the quadratic variation, if we look at this expression, well, as long as we have this condition, you know, if I have a continuous function and I take the sum of squares on points like this, then, you know, as long as the function is continuous, the sum of squares will converge to 0, right? So the only thing that's going to matter here is going to be the jumps. So for us, what we'll have is that the variance is just going to be the sum over I and the sum over t in jump in the jump set of the ith coordinates. And here we'll have just the square of the difference over that jump, which is f at b t plus minus f at b t minus squared. Expectation. Okay. And if we look at this thing, what is this difference between those values of f? So, you know, suppose our process bt was at this point. When it jumps, it almost surely it only jumps in one coordinate at each time. So we basically compare the value of f here to the value of f. Maybe it jumped in, you know, this horizontal coordinate. The difference between the value of f here and the value of f here is just, I can write it as just, you know, the gradient of f. And now this is a continuous gradient. It's not a discrete gradient. It's the gradient of f at b t dot or maybe instead of dot, let me just say, it's the ith derivative of f at bt times the distance, which is 2 times t, right? And this is what we're gonna square. And now this expectation is just going to be over whether or not we jumped at a particular time t, and using this fact, I know how many times we expect to jump at any point in time t, and it just corresponds to this integral. What we'll get is that this is just going to be the sum over I of the integral between 0 and 1 of the expectation of this square times 2t squared times the probability that we jumped. So I'm now replacing this sum by, you know, the expectation of the indicators of the jumps, which contribute a term that looks like 1 over 2t dt.
Just to make sure, the integral is between 0 and 1, not 0 and t, right?
0 and 1. Thanks. Yes. Okay.
And
yeah, please.
And we're computing variance of f of b of 1, right?
Yes. Sorry, of f of b at 1. Of course. Right.
And then in the first right-hand side, it's b of t plus not 1, right? It's like plus a little right after the jump and right before the jump, or?
Yeah, it's just t plus and t minus is, yeah, right after and right before. There is no 1 here. This is a closing brackets.
Yeah, thank you.
T minus, yeah. Okay, so this, we got some formula. I mean, let me write it a bit differently. It's the integral between 0 and 1 of the expectation. So this 2t square cancel, this t here cancels out with one of those things here, and we get, 2 times the expectation t times the norm of the gradient f at bt square dt. Now, this expression is not new, and it can actually be derived by applying the usuality equation. You just have to figure out what this thing means. But the new thing in our analysis is going to be that we don't actually have to look at expectation. We can just do a pathwise thing. We can try to figure out what this process looks like along a given path. Okay? And let me try to give you a flavor of how to do this thing. So I think I have less time than I had planned to have reaching this point. I think I'll try to give you an idea. We're going to forget, let me go up for a second. We are going to forget about this inequality because I'm not going to have enough time to tell you how to prove it. I think I'll try to give you an idea of how to reprove this inequality, this strengthening of KKL, using the pathwise approach, so without hypercontractivity. I think this is the best use of the time we have left. Okay? So let's, so we're interested in this quantity, and we're going to define mi of t to be, so we're just going to look at those processes that correspond to the derivatives of f rather than f itself. The derivative of f is still a multilinear function. So those guys are still Martingales. Okay. And what I am going to try to convince you is the following thing. So first of all, note that mi at time 0 is just the expectation. So since it's a martingale, it's the expectation of mi at time 1, which is just the average of the gradient of f at time 1. So maybe let me just write it like this. which is obviously at most the ith influence of f. And this is true even if we put absolute values here.
So why at most? Just make sure I understand the definitions. Isn't this the ith inference? Or you have squares, I guess, right? For inference.
Yeah, it's the triangle inequality. Yeah, there is a square exactly. If it's a monotone function, then this is equal, right? And on the other hand, so I mean, maybe let me write it like this. The square of f mi of 0 is at most the square of the ith influence of f. On the other hand, the expectation of mi of 1 squared is equal to, well, the expectation of the squared of the ith derivative of f at time 1, which is just the uniform measure, squared, which is exactly equal to the ith influence. So what we have here is, now let's assume, you know what? Yeah, let's assume without this, we're not gonna lose anything here, that mi of 0 is bigger or equal to 0. Okay, it's not gonna matter at all. I mean, even assume the function is monotone. This is not going to affect generality almost at all. The picture looks like this. So mi of f is a martingale such that at time 0, this martingale is equal to the ith influence square. At time 1, this is time 0. At time 1, this martingale, well, it's equal to either 0 or 1, obviously, because at time 1, we know whether the ith derivative is, 0 or 1 at the point where we reached. And in between time 0 and time 1, it looks maybe something like this. So it's a martingale. It starts from a small value, and it ends up either at 0 or at 1. Again, we're thinking about a monotone function right now. Otherwise, it could also be -1, but it doesn't matter so much. Okay? The main thing that we're going to prove is...
Ronen?
Yes.
Sorry, isn't the starting point I of f? Why is it a square there?
Yeah, there's no square. Thanks. Sorry about it. It starts at I of f. It finishes at either 1 or 0. It's at 1 with probability I of f. Yeah, sorry. And what I want to claim is that conditioned on the fact that it does reach this high point 1, all the movement is going to be somehow very close to time 1. So the likely scenario is that it's not going to move at all up to some time 1 minus delta, for delta very small, and only then it's able to start moving and actually decide where it goes. And the reason, and somehow the main inequality that we're going to see here is that So maybe let me write it like this. So this is called, it's a pretty simple inequality. It's called just the level 1 inequality. But it's going to translate into some very nice property about this martingale. So there's an inequality saying that the gradient of f, so maybe let me say it like this. If f is if it's positive and bounded, then the gradient of f at a point x in absolute value is at most f of x times root log 1 over f of x up to some constant. And this is maybe a good way to think about it. So if f is the harmonic extension, and okay, I guess there's another the constant here depends on the infinity norm of x. Think about points which are not very far from the origin, or maybe ignore this constant. It's not going to matter so much for our proof. Let me just try to quickly explain this inequality for x equal to 0. The gradient of f at the point 0 is just equal to the integral of x times f of x with respect to the uniform measure. This is just due to the fact that, I mean, okay, I guess you can just check it. It's like a summation by parts thing. It's the gradient of a multilinear function. Taking the gradient is like multiplying by an x. And the point is that since our measure is sub-Gaussian, then if I have a function which is, you know, between 0 and 1, and I want to make that, so this thing is just, you know, the center of mass of, you know, if f is 0 is just 0 of 1, then it's the center of mass of the set f equal to 1. If I want to make the center of mass as far as possible from the origin, I want to push all the mass somehow in the same direction, and then I really see the sub-Gaussianity of the uniform measure, and we get this inequality. It's the proof is actually like pretty simple, but yeah.
Ronen, this theorem, the main inequality is an inequality that holds for every function. Like what is f here?
So f
it's a multilinear
is,
extension.
So it's the harmonic extension of every bounded function,
okay.
Every positive bounded function. It's gonna hold. And this is somehow, it's a very simple inequality. The proof is, you know, I kind of made a mess explaining it, but the proof is 2 lines, and this is really what replaces the hypercontractive inequality in our case. And what this is gonna imply is maybe just to give you an intuition of why it implies it, let me go back to, this formula here. This formula basically shows you that the quadratic variation is, maybe the quadratic variation, which is really like the rate, the speed in which the martingale moves at any given time, it depends on the size of the gradient of f at this point in time. So if we just take this inequality and translate it to what it means about this martingale, I mean, what we'll get is that the speed, very informally, so the speed that MIT moves is bounded by MIT root log 1 over MIT. Okay, I didn't exactly say what speed means, but speed is just the square root of the derivative of the quadratic variation. This is just, if you discretize this thing and think about the size of jumps of the martingale, the size of jumps will be bounded by this thing, meaning that as long as the martingale is small, the jumps that it's making are also small. Now, the martingale starts from a very small value. I mean, supposing that most influences are small. If the influence is big, there's nothing to show. But if the influences are small, those martingales are going to start from a very small value. And then the level 1 inequality is basically going to translate to the fact that it just cannot, it's kind of stuck in place. There is something that keeps it from moving as long as it's small. And only near time 1, there's like some things can be exploding and our martingale is allowed to move.
There's
so
also
if
a factor of t in the speed, right?
Sorry?
There's also a factor of t in the speed.
There's also a factor of you mean coming from here?
Yeah, like this, or square root t or something. Like there was some.
Yeah, this one I think you're talking about.
Right.
Yeah.
Mm-hmm.
Right, but anyway, like somehow the ideology is that all of the action happens very close to time 1. In other words, if we take a function with small influences and we look at this process f of bt, then f of bt will be, f of bt tells me where I expect the Brownian, this jump process to end, at the point where f is equal to 1 or at the point where f is equal to -1. Almost until time 1, we're basically going to have no idea where we're going to land. Okay, this is sometimes called noise sensitivity. And only very close to time 1, this level 1 inequality is going to allow us somehow to move, which if we go back here, then, this integral, instead of, I mean, that somehow what we get from it is that effectively, instead of integrating here from 0 to 1, it's enough to look at the integral from some 1 minus small delta to 1. This is the only place where you can actually get some contribution from this, and this is where the log factor comes from. Okay, unfortunately, I'm out of time. Somehow online talks, there's I guess it has something to do with the speed of light, right? Whenever I give an online talk, time goes by much faster than I was planning, but I hope at least I gave you some impression about some idea about, you know, what's going on in this proof.
Thank you very much, Ronen. It was fascinating. I guess maybe we can take a few questions. Okay, so maybe let me start. Like, you know, you can think of other martingales that also sort of sample a point in the Boolean cube. Why did you choose this one? Like, how did you came up with this one?
So, I mean, I guess my best answer is a very natural martingale to sample a Gaussian point is the usual Brownian motion.
Right.
And there's many things you can prove by considering this martingale. I mean, many things you can prove on Gaussian space by considering this martingale that, you know, samples a point through Brownian motion. And many of these proofs use the fact that you can take continuous derivatives with respect to time. Somehow, I mean, I guess my main, like if I have to answer in one sentence, having continuous time means you can differentiate stuff. This is like, and maybe the natural, like, you know, and I mean, it seems like this is the natural counterpart of a Brownian motion for the discrete hypercube. I guess this is the.
So let me maybe mention what I had in mind. Like one, like you could take, right? So just like a Brownian motion, and you know you want to make it eventually converge to the hypercube, so you can do like you can slow down if you're coming. Like this is actually your paper that you're slowing down where you're coming close to the hypercube, or you can, you know, have a sticky Brownian motion where you, whenever you reach one coordinates to either 1 or -1, then you stop.
Right.
So like.
So the question is, can you replace this jump process by a continuous process that slows down?
Yeah.
So many of these things, in many of these examples, you can. In the proof that I showed you here, there is like missing. I'd really like to be able to do that, but I couldn't. And the missing piece is that something I kind of skipped over, but there's a log convexity going on. It's pretty easy to show that the expectation of f of bt squared, or maybe let me write it like this, b e to the minus s squared is a log convex function in S. This fact is like actually super easy using, like, if you write this in Fourier, it doesn't matter so much. And like this this thing, I don't know how to extract this fact when we're not doing the jump process. Other than this, somehow everything goes through even in a much nicer manner.
I think we have another question in the chat.
Right.
Technique allow to prove the log Sobolev inequalities.
So, I mean, yes. So basically, you can derive hypercontractivity from this technique. So you can basically show that this what I called level 1 inequality can be integrated along the process, and this gives you hypercontractivity. And hypercontractivity is equivalent to log Sobolev. I'm not sure if like this is what you meant, but
so I guess going back to Avishai's question, the choice of B of t equal to t was somewhat special, I guess. You could have said B of t equal to t squared, or
yes, but this would just be, you know, some reparameterization of time. So as long, I mean, the point is that all of the coordinates are equal. So you know, it's kind of like cheating in the sense that, you know, I'm telling you that you're inside the continuous hypercube, but you're really only on these lines. And
right.
like one thing to notice, which I didn't say, is that, you know, when you're on for a specific time t, you're basically sampling from a noisy version of f. So the points here just corresponds to, you know, a noisy version of f. So I mean, in this sense, this process is just sampling from noisy versions of f, but like the important thing is that you have this special coupling between, it's not like you just consider different levels of noise, you couple between them in this very natural way that gives you a Martingale.
There's another question in the chat.
Can you define a Martingale? Yeah, I mean, you can. So, okay, if all the biases are of the same magnitude, then it's very easy. So if I want all of the coordinates to have, you know, some same bias p, I just don't start my process from 0. I start it from that point. So, you know, if I start my process from this point and just continue as if, you know, it walked up to here, and then from here I'm doing the same thing again, I'll get exactly the biased process. And everything we did here also works for biased measures, essentially.
So the difference is that you don't start in the origin, but you start in a different place.
Yes.
Right? Okay, so I see that questions are asked in the chat, so not all participants can see them. So maybe
so maybe so maybe I'll read the question out loud before answering. Can this approach apply to non-Boolean functions directly? I mean, almost none of the things I said use the fact that the function is Boolean. In all of the proof I gave you, the only place where I use the fact that the function is Boolean is that here at time 1, the derivative has to end up at either 0 or 1. Everything else works just the same if the function is not Boolean. Another question. So connections to continuous greedy algorithms. Very good question, but I haven't thought about it. You know, it kind of makes a lot of sense that you can, like, you want to maximize some variance, so you go along the process and then you choose, like, in a greedy way in which directions you sample first, or I don't know. I mean, I guess it's a natural thing, but I don't have anything clever to say. is there any implication for first passage percolation? So a consequence
Ronen, are you still here?
This computer seems to have slowed down.
Right.
Can you hear me?
Yes, now
yes. Yeah, I'm sorry. My computer just ran out of battery. It said 20% left 5 minutes ago, and I assumed those 20% are going to be enough for 5 minutes, but apparently no. Yeah, so let me just answer without the board. Sorry about that. So this the short answer is I don't have anything rigorous to say about first passage, anything new and rigorous to say about first passage percolation, but it does give some characterization of an event that has to happen if this Benjamini-Kalai-Schramm bound is tight. So since we characterize the stability, that we basically characterize the sharp cases of Talagrand's inequality, this immediately gives some characterization of this, of what happens if this result on first passage percolation is sharp. I guess I could talk more about that, but it would be hard without, making all the definitions. Are there more questions? I can't see the.
Yeah. So I have a question. I don't know if this is a short answer, but it seemed like you applied essentially the same inequality on every path of your Brownian motion of the way you sampled, but somehow still looking at the granularity of paths was useful. Like it still was. Why?
So yeah, that's a very good question. So in everything I showed so far, you can somehow bypass it, and you don't really need to use anything about the granularity of paths. But for the stability version, for the actual versions of the theorems, it's important. So you're really using the fact that if everything is sharp, there has to be at least one coordinate that, with a non-negligible probability, reaches a high value in its effective influence in the gradient of f. So maybe let me put it like this. Okay, let me put it like this. The variance of Martingale is equal to the expectation of the quadratic variation. And this is nice. It gives us things about the expectations of the integrals that we wrote. But we actually know much more. We know that not only in expectation the quadratic variation is large, but also with high probability it's larger than a constant. So with high probability over our path space, we see a path where the gradient has to be large at some point. And this is something that, so you definitely can't get everything just by taking expectations.
And for us.
That's great. Thanks. Yeah. All right. So the next talk will be the next Wednesday by ST on random restrictions. Right. See you all next Wednesday and Tuesday at 10 a.m.